Greetings. So another problem that comes out of antiquity that the Babylonians worked on would be the theorem of Pythagoras, right triangles. And we know a couple of things. This is why I say that we know knowledge from the civilization between the rivers must have migrated west at some point, is the fact that we also know that this same knowledge would be well established and utilized by the Greek civilization, namely the mathematician Diophantus. So there's a very good chance that some of this knowledge that the Babylonians are writing down would find its way into Greek culture, or at least the foundations of some of this work would get to Greek culture and the Greeks would expand upon it. Let's take a look at our favorite equation dealing with right triangles. And as we have come to know and love it, a squared plus b squared is equal to c squared, or the sum of the squares on the legs is equal to the square on the hypotenuse. Now, for our sake, what I'm going to do is I'm going to manipulate this problem, and I am going to divide everything by a squared. And the reason for that is I'm going to get 1 plus b over a quantity squared is equal to c over a quantity squared. And I'm going to rewrite that one step further and have c over a quantity squared minus b over a quantity squared is equal to 1. And I do all of that because of an algebraic identity that I know. I know if I have x squared minus y squared, I can write that as the sum of x and y times the difference of x and y. And that was why I just did all the arithmetic I did. And since this comes from a right triangle, and it would not make sense to have the length of a side of a triangle being 0, I'm okay with dividing by a. So because of this, I'm now going to work on this problem, and permit me to rewrite this now as alpha squared minus beta squared equals to 1. So if I do the factoring, I get alpha plus beta is equal to alpha minus beta, which is equal to 1. Now, the Babylonians would realize, hey, we've got lots of multiplication tables that deal with how to get to ones, dealing with reciprocals. And so we understand that if I have two numbers that multiply to 1, one of these numbers has to be a rational number, namely an m over n, and the other one must be n over m, because that's the only way I get to 1, is if these two factors are reciprocals. Therefore, alpha plus beta is the reciprocal of alpha minus beta. Now, that's a fascinating piece of information. Now, let's take this a step further now. So we know that m, and I'm just picking m and n to say, all right, this one's going to be m over n, this has to be its reciprocal, I multiply them, I get to 1. How does this help me? Well, I now know that alpha plus beta equals m over n, and I know alpha minus beta is n over m. I'm going to add those two equations together, and I'm going to get 2 alpha. Betas go away is going to be m over n plus n over m. Common denominator is going to be mn. So I'm going to have m squared plus n squared is 2 alpha. So alpha must be equal to m squared plus n squared over 2mn. So what you say? Well, now let's take these two equations and subtract them. And I'm going to have alpha plus beta is equal to m over n. Alpha minus beta is n over m. And if I subtract, the alphas go away, leaving me with 2 beta is m over n minus n over m. So 2 beta is equal to m squared minus n squared over mn. So beta must be m squared minus n squared over 2mn. But remember, alpha is what? Alpha was the letter that I chose to put over here to represent C over A. So basically what I'm saying right now is I'm going to switch colors to highlight this. This is C over A, just as this is B over A. Now because of that, and I know these are rational numbers, I know certain things. Because the A is the same in both pieces, I can say in my original Pythagorean identity that A must be 2 times m times n, where m and n are integers. I know that B must be equal to m squared minus n squared, and C is going to be equal to m squared plus n squared. And well, the question is now, what do we do with this? Well, this is how we come up with all of these ideas of Pythagorean triples. And we have an example in a museum of exactly this. A clay tablet with 3 columns of numbers running down it, showing us exactly what's taking place. All I need to do is plug in the appropriate numbers. Now, the Greeks would take this even further and realize I can use any numbers I want as long as m squared is greater than n squared, or m must be greater than n. But I should be able to plug in any numbers I want as long as I can do that. So if I let m equal 2 and n equal 1, I should be able to get a Pythagorean triple. Let's see. 2 times 1 is 2 times 2 is 4. 2 squared is 4, minus 1 makes 3. And 2 squared is 4 plus 1 makes 5. And 3, 4, 5 is a right triangle. And this will work, like I say, as long as your choice of m is greater than your choice of n. And that way you can generate a list of triples. And this is the same thing that Euclid would put in his elements. He would have the Pythagorean theorem, and he would have a methodology for finding 3 numbers that can be the lengths of sides of a right triangle. And if this isn't making you just as happy as can be, you may not should be a math major. Because this is pretty exciting stuff considering it's about 3,500 years old. Wow. I hope this helps.